mathematical model of the flow process. Inflow rate is Wi, outflow rate is W naught. Upstream pressure is Ui, downstream pressure is U naught. Downstream pressure is U naught. Here, there is no accumulation here. In pressure process, if you consider the pressure process, this is the process variable U, this is upstream pressure, this is downstream pressure, but here accumulation is there, but here no accumulation. That is the difference between pressure process and the flow process. Here also we considered inflow rate is Wi, outflow rate is W naught. We know that the inflow rate equal to J1 A1 square root of Ui minus U, where Ui is the upstream pressure, U is the downstream pressure, and M is the valve opening. Directly proportional to M, directly proportional to J1 A1 square root of Ui minus U. U is the downstream pressure. Pressure difference between them is Ui minus U. A1 is the area of cross section of this tube. J1 is the constant of proportionality. Or we can write this as Wi is function of Ui, U and M. Similarly, we can write outflow rate equal to J2 A2 square root of U minus U naught. But there is no accumulation here. There is no accumulation here. There is no mass storage inside the tank. Whatever entering is leaving. Therefore, W naught is function of U and U naught. We know that if you plot between upstream pressure and flow rate, it will be like this, a nonlinear relation. Suppose you are operating at nominal upstream pressure and nominal flow rate. You can find a linear relation. This is a tangent to this nonlinear relation. For small changes, we can consider both relations. So let us consider the tangent to linearize this. Similarly, if you consider the downstream pressure, what is downstream pressure? U is the downstream pressure, Wi is the flow rate. In that case, this is the relationship. If you operate at U nominal, Wi nominal, this is the relation. This is 1 by R, R is the resistance. Slope of this line is minus R. Slope of this line is minus R. Slope of this line is Ri. If you find the total differentiation for this dwi equal to dou f by dou ui dui plus dou f by dou u du plus dou f by dou m dm at nominal, that is at nominal operating point, the value of dou f by dou ui is 1 by ri, 1 by ri, because f equal to wi dui plus dou f by dou u is r, therefore minus 1 by r du plus dou f by dou m is val gain, change in flow rate with respect to opening, therefore kv dm. Let us assume that at nominal operating point this infinite small changes is true for small changes, therefore delta wi equal to 1 by ri delta ui minus 1 by r delta u plus kv delta m. Let us call this wi as small wi. For change in wi is called small wi equal to 1 by ri small ui. Change in ui is called small ui minus change in u is small u plus kv small m. Let it be 1. Similarly, we can find the same type of relation for this, that is dw naught equal to dou f by dou u du plus dou f by dou u naught u naught. Here, as far as outflow rate is concerned, u is upstream pressure. The u is upstream pressure. That's why you will get positive slope. That's why 1 by r you will get positive slope. 1 by r. Let us assume that it is true for small changes, delta w naught plus this is 1 by r naught, but minus. Why? Because it is downstream pressure, slope will be negative. That's why 1 by r negative u delta u naught. Therefore, the relationship for this is small w naught equal to 1 by r u small u minus delta u is small u, delta w naught is small w naught, 1 by r naught u naught, let it be 2. If you add these two, we will get change in inflow rate plus change in outflow rate equal to 1 by ri ui small ui minus 1 by r u plus kv m from the first relation we got, from the first relation. Second relation, if you see, 1 by r plus 1 by r u minus 1 by r naught u naught, these two getting cancelled. So we can write there is no accumulation here, no accumulation. Whatever entering here is leaving here, no accumulation. Therefore, wi equal to w naught. Therefore, small wi equal to small w naught. So we can write this equal to 2 times w, where wi equal to w naught equal to w. So 2w equal to 1 by ri ui plus kvm minus 1 by r naught u naught. Or we can write w equal to 1 by 2 ri ui plus kv by 2 m minus 1 by 2 R naught U naught. 2 Ri is also resistance. That's why we can call this as 1 by Ri dash Ui plus Kv dash. Instead of Kv by 2 can be called as Kv dash M minus 1 by R naught dash U naught. If you take Laplace transform, you will get W of S equal to 1 by Ri dash Ui of S plus Kv dash M of S minus 1 by R naught dash U naught of S. So let us assume that there is no change in upstream pressure and change in downstream pressure means by manipulating M, we can manipulate the flow rate. By simply changing the valve opening, we can change Ws, that is flow rate can be varied. Here, Wi is the flow rate, already I told you that's kg per hour. Kg per hour. Therefore, the mathematical model is outflow rate, that is W of S upon M of S, valve manipulating the valve, that is valve opening, equal to Kv dash. What is the order of the system? Zero order. There is no dynamics involved. Mathematically, we got zero for flow process. Suppose there is no valve changes, but the upstream pressure is changes. If you assume this is constant, this is also constant. If you assume, we can obtain a changes for upstream pressure, that is disturbance model. What is that? This is equal to 0, this is also equal to 0. No changes in downstream pressure, no changes in valve opening. In that case, what you will get is W of S, flow rate upon upstream pressure, equal to 1 by Ri dash. Similarly, if you assume this also equal to 0 and this can be considered as changes means what you will get is W of S upon U naught of S equal to 1 by R naught dash. So this is the mathematical model. If you consider manipulated variable, if you consider the manipulated variable M, this is the mathematical model of order 0. Input is M of S, output is W of S. If you consider this as mathematical model, disturbance model, Ui is the input, output is W of S. If we vary the downstream pressure minus 1 minus, if we vary U naught of S, you will get W of S. So these two are disturbance models. Disturbance model. This is also disturbance model. This is called input-output model. This is called input-output model. In pressure process also we have seen this is input-output model. This is input-output model. This is disturbance model. This is also disturbance model. Here we are varying upstream pressure. Here we are varying downstream pressure. Here this is for change in valve opening. This is manipulated variable. This model is called input-output model, disturbance model, disturbance model. The same way here also, this and this are disturbance models. But for all the changes, if you want a total change, you can add all these together for total change. That is W of S. For change in valve opening, that is input-output changes. Disturbance changes, upstream pressure change, downstream pressure change.